All right. Good afternoon. So what I'm going to be talking about is in line with what the panel was discussing, which is drug discovery. The only difference is with no use of AI. So I do traditional drug discovery. So I'm pharmacist by training. I have a PhD in drug design, drug discovery, and medicinal chemistry. And current interest is to find new drugs, new anticoagulants to treat venous thromboembolism, VTE. And, as far as the impact of venous thromboembolism, or before that, I mean, what's venous thromboembolism? It's basically things like deep vein thrombosis, pulmonary embolism, even the most recent pandemic, many of those who basically passed away because of COVID-19, it was because of a complication of pulmonary embolism. So clotting is a defense mechanism, right? But then if it goes beyond what we expect it to do at other sites, that's where it becomes pathological. This is a slide where we have basically the impact of venous thromboembolism. We have estimate of 100,000 deaths per year in the States attributed to the VTE. There is a recurrency there despite the current treatment, and there is enormous economic burden, right? Of course, other areas where we can use these molecules, where we have, these surgeries for knee replacement, hip replacement, because we know we introduce these surfaces, foreign surfaces into the body, and we know for sure they're going to trigger clotting. Therefore, most of those who undergone the, hip or knee replacement, they have to be put on anticoagulants. Now, the question is, do we have anticoagulants? Of course we have anticoagulants. I mean, we know warfarin for more than 100 years. We know heparin for more than 100 years. Heparin was introduced to the clinical practice before FDA existed, right? And recently we have much better drugs. We have specific factor Xa inhibitors, rivaroxaban, apixaban, edoxaban, betrixaban. We have thrombin inhibitors. Yet we continue to have the same problem, right? So we, as people interested in medicinal chemistry, drug design, we try to find problems related to current treatments, and we try to address this by doing drug discovery. In other words, we would like to design, develop new molecules that could deliver the same efficacy or potency in the treatment, yet does not really suffer from the same side effects. Now, what is the major side effect for the drugs we have right now is basically the major side effect for all currently available anticoagulants is the internal bleeding. I mean, the bleeding could be to the extent that the patient steps into hospital and loses his life, not because of the clotting disorder that he was diagnosed with, but it is because of the side effect of the drug he was put on. And this is for all of these currently available anticoagulants, whether they were old or new, traditional or non-traditional, specific or non-specific. Now, mechanistic reason for this is the representation for the coagulation cascade. Basically, the coagulation cascade can be identified with the extrinsic coagulation pathway, where we have factor 7A, intrinsic, where we have 12, 11, and 9, and the common coagulation pathway, 10 and thrombin, right? So all of what we have currently targets two proteins in the coagulation cascade, and that's factor 10A and or thrombin. It's like you try to get to the business district of New Orleans by approaching one main highway. You have two branches to that shared highway. If you block one, you keep the other open. Still, there are individuals who can reach the business district. But if you block the main highway, Nobody will get to the business district. And in this case, all of what we have right now, they block proteins in the common coagulation pathway, which means they block the ability of the patient to clot under healthy conditions and non-healthy conditions. In other words, they block the pathological clotting and the physiological clotting. Remember, we have something called hemostasis. Hemostasis is a defense mechanism. We needed to clot, you know, in case we got into accident, right? We need that. But if we use these drugs, we lose that ability. So yes, they treat by stopping the pathological conditions or the pathological clotting, but they also block the physiological clotting. And therefore, yeah, you treat, but the blood will keep flowing. And therefore, there's accident or anything, there will be bleeding. And sometimes without provocation, you could have that bleeding. So what is the solution for this? The solution is to target proteins that are not involved in the physiological clotting. We target proteins that contribute to only to the pathological clotting. And you know, epidemiological studies, clinical observations highlighted 3 proteins, which basically I'm currently working on to develop some molecules. We have factor 12A, 11A, and factor 13A. So this project is about targeting factor 13A. So factor 13A is very different from all other clotting factors. All other clotting factors are serine proteases, proteolytic enzymes. Factor 13A is a transglutaminase enzyme, which means it does cross-linking. The clot is produced without factor 13A, that clot is fragile, can be easily digested. So in order to form a rigid clot, you have to have factor 13A. So the hypothesis was develop something that inhibits factor 13A. You will keep the patient ability to clot, but the clot can be easily digested. Now, that was the hypothesis here. We could block the formation of rigid clot, so we could basically perhaps strike a balance where we treat but don't cause bleeding. This is basically in vivo proof of concept. It was with the use of peptide. And you can see this is a rabbit model of venous stasis. And here is the peptide. As you see, the use of the peptide restore the flow rate in the jugular vein, right? Restored after that clotting was provoked, induced by stasis. This molecule, which is specific factor 13A, was able to restore the flow rate. You have the weight of the thrombi. It's right here, and you see that the weight of the thrombi is less. Means that thrombi in the presence of that specific factor 13A is smaller. And then this is the model where we test the ability to provoke bleeding. And you can see that there is no much bleeding by the use of this. So using this model, we thought specific factor 13A inhibitors would do it. So we designed molecules, specific molecules to target factor 13A. We do biochemistry, that is transglutaminase or transglutamination inhibition assay. We do selectivity over other clotting factors. We confirmed the results of 2 molecules, as in they actually block factor 13A, and they block the cross-linking process of fibrin. Of course, we have to make sure that the molecule is also selective over other transglutaminases, and it is here with respect to transglutaminase 2. Mechanistic study using mechanistic kinetics as where this molecule binds. Does it bind to the active site or allosteric site? We were interested in designing allosteric sites. We developed molecular model in order to know, I mean, we don't have really mutants thus far, We don't have access to structural biology. So we did modeling. And we tested the molecule, for cellular toxicity. So eventually we were able to identify two molecules we think they are very specific to factor 13A inhibitors, selective, non-toxic. It just, upon availability of resources, we would like to advance this molecule to be tested in animal models. These are potentially used for factor 13A inhibitors. And this project was funded by a grant from NIH, R16. Once again, as I said, we are trying to advance this molecule to more pharmacological work and pharmacokinetic work.
Thank you very much. And we're about to have a break, I think, in about 20 minutes. So if you have any questions, you can absolutely come and talk to Dr.
Sure.
Al-Horani during the break. Thank you, sir.